Good evening and welcome everybody. This is Obi-Wan Pez for N-Simplex Pachinko, and we have differential equations tonight. We're joined currently by Zach at e to the 2i pi. If you'd like to say hi and introduce yourself.
What's up? I'm Zach. I think this is what, day 15,
15,
17?
yep.
Is it 15? Okay.
15.
So, yeah, I've been here, I think about half the time. Just with my dissertation and all that. I wish I could be here more, but I'm here to sort of help out where I can and discuss some differential equations. It's going to be a good time.
Woohoo! And we have in chat Laz, how's it going? Stucky, oh yeah, no worries. Completely understood. We have Enigma in our chat here as well. And thank you so much, Enigma, for the use of the bot, because it's been a big help to every single one of us, I know. Yup. Speaking of the bot. Alright, so tonight our discussion is going to start with... Now, where did I put it? Pictures. There we go. Oops. This is fine. Here we go. Alright, what are Newton's laws?
Are we talking loss of motion?
Yes.
Okay. I
That's
just want to
true.
make sure.
That's true.
Gotta be careful. Okay, Newton's laws. So, well, let's see here. We can talk about them. Let's see. So first, there are three. First, you're gonna have that an object tends to stay in motion until acted upon by a net unbalanced force. You might call that the first law, or the inertial. Speaking of inertia, an object basically has inertia. I'll let you write that down. I don't want to go too fast.
Okay. So essentially, objects maintain momentum unless they're going to be acted upon by forces, at which point that momentum can change. Specifically, we're looking at velocity, but, you know, I guess it could change its mass.
Mm-hmm. Yep. So then, the second law is encoded by a relationship that the sum of the forces on an object is equal to the mass times the sum of the accelerations. Sums of mass and accelerations. We should have the M, I think, together with the A.
Okay, just in case.
Yeah. We could even just say it's M times A. I don't even think we need the sum on the right, at least. So it's essentially if you have a whole bunch of forces acting on something, that sum needs to be proportional to mass times the acceleration. Or it's equal to the mass times acceleration, not proportional.
Yep.
So it would be K, right? And then that's speaking to the sum of forces. And then the third thing is that you have the equal but opposite force will always exist, right? If you apply a force to an object, you're going to have an equal but opposite direction facing force on it. I'll let you word that however you like, but that's the basic idea. If I remember my mechanics from what, it would have been nigh into 20 years ago. It's pretty close to that. I remember my freshman year as an undergrad.
Yeah, that's maybe not the best wording.
I didn't say it the best, but I'm going off of memory. I'm actually trying not to look it up. I'll look up the actual wording here. But
equal and opposite
those
reaction. We know the fancy or the colloquial.
Yeah, I know the equal
wording.
and opposite reaction thing, but the opposite force, the opposite direction, is really what it's getting at. So if there's the sum of forces should be 0. I'm gonna do the official lookup. How did I do? See if I missed any details. So Wikipedia says the body remains at rest or in motion at a constant speed in a straight line, except insofar as it is acted upon by a force. That's in essence what we had. The second, at any instant of time, the net force on a body is equal to the body's acceleration multiplied by its mass, or equivalently the rate at which the body's momentum is changing with time. mdv/dt, if you wanted to.
Mm-hmm.
Or d. Yes, I did say that correctly. P. What is it? It's no. That's right. mdv/dt. That's right. Okay. If two bodies exert forces on each other, these forces have the same magnitude but opposite directions. That's right. Okay, so we did get all 3. Good. Makes me feel better being validated by something else.
Something like that. Alright, system must be balanced. If I'm pushing on a chair, the chair is also pushing on me in order to make sure that the system is balanced in all directions and we don't have some weird force appearing out of nowhere. Okay, well, interestingly enough, Actually, you know what? Let's ask the other question. What was another Newton's law that you might have thought
of? So there's like Newton's. There's some stuff he's done with optics that I'm thinking of. Trying to remember.
I don't know those offhand, so feel free to look them up.
Like I was gonna say, I'm remembering he's done work with optics. He has those are the 3 that are like the commonly known stuff. You have stuff that he's done with like we don't call them laws, but he's done stuff with harmonic motion, center of mass. Those aren't laws. Yeah, nothing comes to mind.
Yeah, I've got rectilinear propagation, refraction, and reflection.
Law of refraction. Yeah, that's what I'm thinking of with respect to. I'm thinking of laws of refraction. I mean, there's Snell's law, which isn't a law of Newton.
Yeah, that one's a cool one.
Talking about the sine of angles is proportional to the medium constant, if you will.
Mm-hmm.
So there's some fun things to do with that, but that's its own topic for another day. You can get it like why rainbows have a certain incidence angle and so on. That's a fun
approximately 30
optimization problem
degrees
for another day. Yeah, approximately 30, 32, something like that.
Yeah. Yep. Which, right, reflection and refraction actually kind of go into Snell's law.
Right.
Because for the most part, for a reflection, angle in equals angle out. And like that's all you need. But at the same time, if you don't have a perfect mirror, if it does refract it in any way, Snell's laws apply, and so you just go with that. The other one that I was thinking of was gravitation.
That's right. So you have the universal law of gravitation, which says that you have the force of gravity times the product of the masses divided by the radii, I believe.
Yeah, or
the radius,
whatever you want to call it, the distance between them. So
that's right.
Usually d squared because you're talking distance. R because we're thinking in terms of like planetary bodies. Some people might be like, oh, the radius of the planet. No, we don't want to do that.
Right.
So it's going to be the distance between their centers of mass individually as bodies. What's that? What's that distance?
Yeah, and it's the inverse square law that this applies to. So that's why you have a square at the bottom is generally the square of the distance.
Yep. And that's one of the other interesting things about it is like as both, I mean, this is light as well behaves in the same way. As we start going out at a particular angle, we see that both gravity and the amount of light coming off an object will fall off by this square of the distance because we're looking at not a just one-dimensional distance that it's traveled, but rather the concentration of the light is really what matters. And so we see essentially the individual photons beginning to spread out as space, as we move away in distance, which means that the area of the cross-section of your particular, well, I guess your eye in this case, is going to receive a differing amount of light based on your distance. Again, distance squared. So it's a really cool thing. Yep. All right, cool. Glad you found it, Enigma. I should have everything up there. That has been perhaps a slight embarrassment of mine there. That's all right. Okay, cool. Yep, 28th. All right. And as it turns out, gravitation works the same way. I don't think anybody really quite understood why, but it kind of seemed to behave the same way as with light. I think most people were thinking, like, it's just the distance between these two objects. Why should it be squared? And I think now with the understanding that gravitation is at least helped along by the Higgs boson, that it acts more like a particle, a force-carrying particle. And so in this case, we see that, well, if it is moving out like a string of particles, then it's also going to spread out in the same way that light does.
Well, and something I was doing a little research on this just now, and there's a sense in which we're like when you that when light travels, it travels in 3 space, and the radius of the sphere, as light propagates out, is proportional to 4 pi r squared, the surface area. And so you get this square term. You have a constant, right? This 4 pi, but then the r squared comes from the fact that surface area growing radially square of the radius. So therefore, this notion of like a cross section almost with respect to radius, like we have these like concentric spheres. That sort of explains why you're going to have the r squared in the denominator. sort of an interesting idea.
I used to be really into astrophysics, so like learning all about some of that stuff was kind of my primary goal in high school.
Nice.
All right, so question 2. Which of these represents a differential equation and how?
So, in my mind, the one that's literally written as a differential equation is number 2. I mean, 3 tells you that there's balance, right? So you have a force and its opposite summed to 0. That's reasonable. It's not strictly speaking a differential equation since there's no literal differential in there.
Yep.
And then inertia isn't in its writing a. It's not written as a differential equation. You might be able to finagle it if you try, but you'd have to try pretty hard, I think. I love that.
It's almost like we coordinated, but we actually didn't.
No, that was not that. I didn't do that on purpose. It was just in rereading the Wikipedia version that I said that.
Gotcha.
And so
but
I didn't even
right?
think. I didn't know where you were going with that. So to be honest with you, I was like, I'm just gonna say this. No, it's true. I don't know if it's helpful. But apparently it was helpful.
Yeah. So Newton's second law of motion's like the one that's the most obvious, even if, you hadn't said immediately dv/dt. If we think back to how we understand our acceleration acceleration in terms of differentials, like we had been talking about at the beginning of our semester here. If we think all the way back to Calc 1, when we start talking about motion in general, we almost always bring up the fact that we've got x of t is our position function. We've got x prime of t, which we also call v of t, is our velocity function. And then x double prime of t is v prime of t, is a of t, which is our acceleration. So yeah, as soon as you start looking at differential equations and remembering how we started out with Calculus 1 in terms of trying to find all of these equations, and if we'd started out, I know we did a bunch of stuff in my class with just planetary, or not planetary, but ballistic motion. So throw an object in Earth's atmosphere, what happens? Again, we tend to approximate the path of an object as a parabola, whereas that's not technically true. It's close enough that nobody cares that much. And especially since it really simplifies the mathematics down so that we can explain this to middle and high schoolers without somebody having a stroke in class. So, when are we going to talk about the Coriolis effect? Yeah. Arg. Okay. So really what we were looking at is, well, now this means that the sum of all of our forces as vectors, and most of the time we're going to deal with one-dimensional stuff, because otherwise it's going to start becoming a much larger two- or three-dimensional system, and when all that happens, we get a lot nastier differential equations. So the sum of our forces as vectors is going to be equal to m times, again, this was a of t, but we could just as easily write that as v prime of t, or we could just as easily write that as x double prime of t, but again, we can... Yeah, okay. So then, what kinds of relationships do we see in kind of standard physics classes and things like that that are forces?
Sorry about that.
No, that's fine.
So when you think about force, you can have like I mean, it's like almost. Why do I blank on the question that's like everything's a force, right? But not everything yet. Like if you apply like a mechanical force to something, you can have a you can, when you press the gas pedal on your car, you're applying a force. Gravitational force is a thing where you're attracted to something. This is what celestial bodies do. Humans, when we're, any creature on Earth that walks on the Earth is being pulled down, right? There's a inherent gravitational force pulling us to the surface. All that kind of stuff. Was that what you're looking for? That kind of thing?
Yeah, I mean, just as an example, right? So we'll pick gravity.
Strong and weak force, if you want to go with Enigma's answer. If you want to go that deep.
Yeah, electro weak. Woo! So at some point we start getting into the fundamental forces of the universe, and yeah, we could do strong nuclear, weak nuclear, electromagnetic, and all this other stuff. I don't have a whole lot of that prepared, so but I do have gravity.
I mean, but forces are usually categorized into those groups. I mean, you're going to get gravity's the most, like, I hate the word obvious, but it is the most, like, ubiquitous one.
Yeah. So it definitely is used on a daily basis. I mean, that's the one your brain is automatically doing calculations for. You throw something across the room and you want somebody to catch it, they're going to be thinking about how it works with gravity. Have you seen the video of the astronaut who's trying to explain something?
Yeah. I think I've heard of it. I didn't actually watch it, but I think I have heard of it.
So he's trying to explain something, and he's like, yeah, well, he's been on the ISS for like almost a year or something like that.
Right,
he's like,
right.
Yeah, well, you get this, you get the ISS flying across the body like this, and then he goes over and reaches for something, and he goes, oh. He just looks around like, what happened? And then he looks down and he goes, oh, right.
Yeah.
Not on the ISS anymore.
Yeah. The other things I was thinking of, like, I was just doing a little bit of a search, just because the thing I was thinking of is how to say if there's a better category. But when you asked the question the first time, I instantly thought of springs.
Yes.
Right? Like,
absolutely.
That we apply springs to things. And I know that's relevant for our discussion. That there's going to be some discussion about that. But there's friction, all sorts of stuff. Magnetic. like you were saying, drag is a force.
And I'm going to say that that's going to be lumped in here.
I mean, you may have different, like, categories here, but...
Right. So, in terms of... Let's go with gravity. What is the easiest, quote-unquote, equation that we typically use for gravity when we're talking about, you know, how to calculate the force of gravity to, you know, middle high schoolers?
What, mg?
Yeah.
F equals mg. That's the one you're looking for?
Right, and what's g?
G is a constant that represents the acceleration on Earth, basically, of an object. So it's 9.8 something. Sometimes people round it to 10, depending on how lazy you are. 10 Newton meters per second squared.
Yeah, so generally speaking, 9.81 is about as accurate as you care to get. It's like 9.809 or something like. I mean, it's close enough, right, that nobody's going to care. And again, if we're approximating this system as a parabola, then approximating gravity as 9.8 or 9.81 is not too bad. All right, how about spring mass systems?
Spring mass, that's Hooke's law, right? So you have the minus kx. Force equals the minus kx.
Right, so oftentimes associated with Robert Hooke, who is the same Robert Hooke. The same Robert Hooke who was Newton's advisor. The same guy who stole a lot of his students' work and pawned it off as his own. So, good question. Is this actually Hooke's law, or is it one of his students? So this is also one of the reasons why... Well, VS Click, if you're interested at all, we are here for actual mathematics. We are doing differential equations tonight, but I do also, on Tuesday nights, we do math help streams for whatever else you want. There is also a large group, large-ish, group of math streamers who are listed here, and you can follow any of the 7 of us here on this list. There are a few more, and we'd love to have you in if you're interested in learning anything. So, yeah, so spring mass systems, Hooke's law, F equals kx. So in this case, our force is proportional to the distance away from our equilibrium position. That the mass is, or the spring has been stretched from that equilibrium position. Again, gravity, F equals mg, is F equals ma, is F equals mx double prime. So the force is based on the acceleration constant, or potentially if there is a variable field. So in theory, if you get far enough away from Earth, you might need that a to be a function of t. And friction and drag. How do we codify that one in mathematics?
Isn't this the minus gamma v, where you have a drag? The drag is proportional to velocity.
Yep.
Or yeah.
Which is going to be our x prime.
Yep.
So typically this is used for like air resistance, but
So, can I comment on this?
Absolutely.
Or this was like a revelation to me when I TA'd differentially. So I got to TA differential equations in my undergrad institution, and I realized why we do this, like the minus gamma x prime.
Mm-hmm.
And the thing that I don't know if you're going to talk about the physics at all, but when you know how you have on a door in many buildings, you'll have a door that when you open it, there's this little device that causes the door to close constantly.
Yes. Did you watch
Right?
that recently on Technology
No,
Connections?
no, I didn't. But I remember when I first TA'd this class, I was like, "What the crap is this negative gamma? Like, what is this doing here?" And what I learned was that's actually why we have what's called a dash pod on our door. It's literally a way of like if I open a door, I don't want the door to swing shut and like do that really fast. I want it to do it at a constant rate so that I don't cause damage to the door.
Mm-hmm.
And so this is meant to be a constant closing forcer. And there's different ways to implement this, but in essence, that's how a dash pot works. Is it'll cause the door to close at a constant rate. Yeah, so it makes drag the same constant in essence. So this gamma x prime is meant to emphasize that we're keeping drag constant. We're not doing anything crazy. So it's more an assumption that's nice, I guess.
It's a convention.
It's a convention, yeah.
Yeah, so I think if you're increasing your gamma, specifically, it's going to be making... Right, it's going to be decreasing the overall force. And so if you're like, oh, well, I'm going to increase the drag on the door, therefore it's going to lower the amount of total force that this has. So I think it works better in terms of intuition. It's much the same way that we do in function transformation. Right, y equals a times f of b times x minus c plus d. Like, why the parentheses, why the negative here? Well, it just ends up in the way that we're describing it. It's more intuitive to say our b is going to be our horizontal compression factor, and our minus c is going to be, or rather, c is going to be the distance that we move to the right. And then if it's just x minus that, we're moving... if it's x minus something, we are moving to the right. And so even though it's a negative number, we're still shifting everything to the right. So when you delve into it, it makes a lot of sense. I think that's the same sort of, like, intuitive reason that we use that negative for the gamma.
And now you know.
Woohoo!
Right?
Knowing's half the battle.
Yeah, I know. G.I. Joe. G.I. Joe.
Okay, so then this means that we've got mx double prime, which is going to be equal to the sum of all of the forces that are going to affect a... If we're going to use spring mass system, if we're going to use gravitation, we can come up with a number of different equations to make this all work. So let's do gravity first. Cool. Unless I just didn't write it down. That's fine. Okay, cool. No, this will work all right. Okay, so Sorry, got the Battle Hymn of the Republic playing, which cool and all that, but not quite the vibe we're going for today. Okay, so our mx double prime is going to be equal to, in this case, we've got the sum of all of the forces. So that would be what? If we're just talking about a gravitational system.
So you have mx double prime, you have your minus x gamma x prime, and then you add on the kx as well.
All right, and in this case, what is our kx doing?
That is the stretch, right? Like that's our Hooke's law.
Okay, so we're doing spring max system.
Yeah, are we? Is that not? Hold on. Maybe I missed your question, but did I?
No, that's fine. I was originally going for just gravitational force, but that doesn't quite work. It's fine. Okay, so if we're... Okay. Yeah, I was somewhere else. It's all right. So if we have some sort of stretched mass system, which came from an equilibrium, let's say here, right, our initial amount that we have, the equilibrium, is going to be, let's say, just lowercase l. And the distance that this has been stretched is going to be our capital L. Then again, the distance that we have on the stretch system is going to be the sum of our two lengths. And if we end up with I'm going to back up just a little bit here. That's all right. So we're going to have first our mg, which is just our force of gravity. Then we're going to have the minus gamma x prime, which is going to be any air resistance that we have in the system. Then we're also going to have a minus k times the quantity L plus x. Right. Spring mass, I forgot. Usually this is also negative kx. Alright, and then we could, in theory, also have some sort of f of t function that's attached to this. And we talked a little bit in our second-order differential equations part that we had just a little while ago, and I think I mentioned it in the first-order system stuff, that an f of t would represent what?
That's your external force, right?
Mm-hmm.
So you have like some. So I wanted to give a little bit of like context on this, or like something. I do have to get going, so I told you I was going to leave. Well, I now know when the events have occurred. So, I did want to say something about this before I go, though. That, incidentally, and I agree with what Aperiodic's saying about the negative, the minus kx. That's how I remember it as well. I just put a video in Discord that is about vibration and resonance, if you're interested in looking at this. But what's fun about this whole thing is this actually explains building physics. Like, this is actually what's in practice used to determine how to engineer buildings. And there's a really cool application. If you're interested in Discord, I've linked to a video if you're interested to see how this stuff is actually, like, in practice makes like a 3-story building work. For instance, you can control everything by a mass spring system, and it's a very good model. Not perfect, but all models are wrong.
Exactly.
Except some are useful.
It is a very useful model.
Yeah. So if you're interested, I got to jump out. And
no worries.
Stuff, but I appreciate you doing this, and I look forward to being here Wednesday.
Well, thank you, Zach. I'll see you on Wednesday, and probably tomorrow for that matter.
Yep.
All right, have fun.
And tonight, I will be back tonight. Actually,
oh, sure.
If you're around,
yep.
We're going to do our part 2 of the review. So get excited for that.
Alrighty. I'll see you later.
Catch you later.
Okay, I was looking to see if my kids had like a Slinky in here or something, because they definitely have one. But so the idea is that if you just have a spring mass system, you're holding something steady like this, you pull this thing down and let it go, it's going to then oscillate with some sort of behavior. Typically in Okay. So with some sort of behavior, it's going to then oscillate back and forth. As Aperiodic says, the force that's exerted on that displaced spring mass system is a restorative force. It wants to go back to the equilibrium. But of course, as we all know, it's going to overshoot the equilibrium and then have to sink back down again to try and get back to equilibrium, but then it's going to overshoot it again, and it just keeps doing this over and over again. Now, if it is an idealized system that has no friction, no drag, no loss to heat, which, yes, eventually does become a thing, even in a frictionless system, the energy that's lost to the spring as a function of heat will count, so it will eventually matter. Like even that amount, if we neglect all possible sources of the loss of energy to the system, the idealized system ends up being this pure oscillatory motion. So we can actually show that through doing this, that we're going to have mx double prime is going to be equal to. Now, in this particular case, if we have equilibrium, then our mg force is going to be equal to the negative KL, or rather KL. It's going to be equal to the KL force. And so in this particular case, those two things are going to drop out from the equation. So we're going to end up with a negative gamma x prime minus kx. And that's it. Yep. Which, when we shift all this over, we end up with mx double prime plus gamma x prime plus kx is equal to 0. Or, if we have the forcing function, that's going to still be over here. So, this ends up being the exact same stuff that we were working with last time. This is our second order linear. And here, this is homogeneous if there is no outside forcing function that's working on it, or if there is, this is the inhomogeneous portion. So it depends on whether we have an outside force that's acting on the spring mass system. So if we're taking... I really want to have a slinky on me. Let me just look at it real fast while I'm talking. So I'm sure there's one in here somewhere. If we're looking at this spring mass system, and if we have a slinky, which is then allowed to bounce, the forcing function would be the motion that you are putting on this this system, or rather the forces that you are imparting on this system, which then change the overall behavior of the system itself. So as Zach was saying, this is actually something that creates resonance, or you can have both... There's a yo-yo, but that doesn't help. Arg. You know, like the one time you need a slinky, right? So yeah, you have this force that you're then imparting on the system itself. I'm sure every single person has played with a spring mass system where you have like bounced it up and down to see if you can make it go flying all over the place, or if you can make it do weird things that just like are completely unpredictable, or you can kind of like bounce it just right that it stays almost exactly in the same place, or just bounces a little tiny bit. Right, so these behaviors of the, yeah, also not the vibe I'm going for. So, as much as I like human suffering, by Loic Farouk Ghanem, not the vibe we're going for. I'm much more appreciative of the jazzy slash lo-fi kind of stuff. Apparently I need to change some of the stuff in there. Okay. So now we have a second-order linear homogeneous differential equation, which is at the heart of this thing. And if there is a forcing function, sure, it's an inhomogeneous part. But we know how to solve that. We just did those. We just worked on that with Zach and Stucky last week on how to come up with solutions for homogeneous second-order linear differential equations. So how do we do that? Well, we went and we said, we're going to look at the characteristic equation of this. So we would let x be equal to e to the rt, or we did it as lambda t. X prime is going to be lambda e to the lambda t, and x double prime is going to be lambda squared e to the lambda t. So what does that do for us? Well, now double checking something. We would take this and plug it back into the differential equation to say what kinds of functions are we going to get? What is our characteristic for this equation? So m lambda squared e to the lambda t plus gamma lambda e to the lambda t, this is fine, plus k e to the lambda t is equal to 0. If we factor out e to the lambda t, we get m lambda squared plus gamma lambda plus k is equal to 0. We know that e to the lambda t can never be 0, so we know that this one has to be. So m lambda squared plus gamma lambda plus k is equal to 0. We know how to solve quadratic equations. Okay, that is lambda is going to be equal to, and again, these are our eigenvalues. It's going to be negative b, which is negative gamma, interestingly enough, right? Because we shifted what side it was on, it made it positive over there. So that's also another reason, Zach, if you're around, our gamma and our k are negative on the other side, because they just get shifted over to become positive. And that way the math works out nicely when you're doing this in this kind of format. Plus or minus square root of b squared is gamma squared minus 4a is m and k is c. I know how that sounds. Divided by 2 times a, our mass. Okay, so now we got our eigenvalues. All right, what do those represent? Well, in a spring mass system, these are going to represent the 3 kinds of equations that we can get, the 3 types of solutions that we can get for a quadratic. We know that gamma squared minus 4mk could be one of 3 things. Right, there are only 3 possibilities here. Gamma squared minus 4mk could be greater than 0, it could be equal to 0, or it could be less than 0. That produces 3 different and distinct behaviors, just like all the other quadratic equations we've ever dealt with. So, what does that mean? Well, again, here, if that discriminant is going to be greater than 0, we end up with a positive value under the square root, which gets us 2 real, distinct eigenvalues. Woohoo! If it's equal to 0, we get a repeated root. And if it's less than 0, then we end up with non-real complex conjugate. All right, so let's think about what this did for us when we were looking at our functions, which, it's all right. When we were looking at our second-order linear differential equations, what did that do for us? Well, when we had non-real complex conjugate eigenvalues, this meant that our system ended up being oscillatory. So we had some sort of oscillation that went with it. Now, in this particular case, we could also then have little parts of our system that are going to cause either reinforcement or, there we go, constructive interference, at which point we have this amplification factor, or we could have a destructive interference, which will cause the whole thing to start oscillating down to 0. Or we could have a pure imaginary system, in which case nothing happens. Or I shouldn't say nothing. This is going to oscillate and only oscillate. It will not get bigger. It will not get smaller. Okay, so here, let's... Right, so our complex conjugate eigenvalues are going to split into 3 cases. We're going to get something that looks like A plus or minus I times omega. which then itself splits into 3 cases. Right? A is less than 0, A is equal to 0, and A is greater than 0. We know that omega is not 0, because otherwise it'd just be a real number. It'd be one of those other 2 cases up there. So if A is if A is less than 0, right, omega is not 0. If A is equal to 0, we get pure oscillation. If our A is less than 0, we get oscillation toward 0 or toward equilibrium. Let's just say toward equilibrium. And if A is greater than 0, we get oscillation toward infinity. Now, ironically enough, this constructive interference does a lot of destruction. So typically you end up with some sort of system in which the object itself will begin amplifying the oscillatory behavior, and eventually it will cause its own destruction. It's going to shake apart. It's going to, knock down a building. It's going to rip the bridge. I know Zach had said that he didn't really want to talk about Tacoma Narrows, but nonetheless, it's overused, but nonetheless, it is an interesting case study. So what about these other cases? Right? What happens when we get 2 real distinct eigenvalues, and what happens when we get a repeated root eigenvalue? All right, just making sure. Okay, that's interesting. So, I'm not getting the... I'm not getting the split on A. Apart from it's either 0 or not. I'm sure there's a reason. I'm just not seeing it at this exact moment in time. probably explore something in here with that in just a bit, but nonetheless. Alright, so with two real distinct eigenvalues, what we end up getting is what's called an over-damped system. And typically the way that this will manifest itself is that if we have some initial starting value like this, basically no matter how it moves from here, if we just call this equilibrium, right, y equals 0 for this case. No matter what the initial motion is, no matter what the initial position is, this thing is basically going to just sink straight down to equilibrium via an exponential function. Now, it can be like launched in a particular direction. In this case, it's starting to move away from starting to move away from equilibrium just in its, like at its, for its immediate locality. But what we see is that it will sink back toward equilibrium very quickly. We could have other cases where, like, if this was launched downward with a speed that makes it go toward equilibrium faster, it can go past equilibrium, but it's going to go straight back to equilibrium as an exponential function. So, I like to think of this as if you put a spring mass system extended outward and then let go in honey. So if you were to let go of that spring mass system when it is in honey, no matter where you stretch it, no matter what initial values you give it for its speed, for its initial position, when you start, you know, clicking your stopwatch, this thing is going to like slow down pretty quickly and go right toward equilibrium. Never gonna viv you up. Yeah, well, thank you. Family's doing pretty well. We're just starting school toward the end of this week, so it's going to be an adventure. We got to stop over at our uniform shop tomorrow and make sure that we have all the last little bits that we need, just in case. Man, it is wild. And as Zach was saying earlier, the I forget what he called it, the something pot that's hung on the top of the door, that has the little, the metal piece and collapses together every time you open the door. It has that little motion to it. That is that is one of these typically overdamped systems where it's trying to make sure that the door is closed with a reasonable speed. But at the same time, and this was talked about in Technology Connections video recently on YouTube, is that you don't want this thing to go too slowly. So if you push this thing open, you don't want it to, like, you don't want the hydraulics in there to act like they are in honey, where it's going to be like, I got to get the door open. A, that's dangerous, And B, it's really frustrating if you had to deal with that. So you want this thing to open almost freely until it reaches close to the end of its swing, right? Maybe you want it to go a little bit slowly at the beginning, but then be able to open up quickly. You don't want this thing to fully open and then go whack against a door, or like, freely openly swing with whatever force is applied to it. You want it to open consistently and close consistently. So an overdamped system might be what you're looking for, just not like super overdamped. If we have a repeated root eigenvalue for this, what we get now is instead something that is critically damped. And the critically damped systems... And I'm sorry, Viv, how are you doing? The critically damped systems, honestly, the way that the book shows it, it doesn't actually look that different from the overdamped system. However, I'm sure that it just moves a little bit more slowly toward equilibrium. So this is going to go up like this, and then it's going to sink down and take a while to get there. This is more like our systems of differential equations that we were looking at earlier, where if you remember looking at the 2D plots, right, our phase plots, the repeated root eigenvalues have one specific eigenvalue, one specific vector that everything is moving toward. And almost everything around it is kind of like moving toward that particular vector, no matter where you are in the space. Oftentimes there's a little bit of a loop around 0, which is going to show off a little bit of... No, I don't have it open. Okay. That's a slope field plotter. Slightly different. Right, so our critically damped system is going to be in that same vein, where it's like it almost reaches a linear decrease toward equilibrium as we get further on. Or in the case of a negative initial velocity, again, this could shoot below 0, but again, this is going to essentially start following an almost linear path to get back to equilibrium. It is going to eventually be exponential-ish, in that it is going to not reach 0, right? It's still asymptotic, but it just takes longer to get there. Let's go like that. Let's go like that. There we go. And no sloppiness. Right, let's maybe exaggerate this a little bit more with this one. So it's going to go down like this, and then it's going to come down like that. Exaggerated. Right, so our overdamped system very quickly moves to this exponential decay model. Gets it to the equilibrium much faster overall. Our critically damped system is almost linear, and this is what Zach was talking about in terms of trying to find a linear closure rate for linear closure rate for the door, when you have that damper on top. Oh, that's not good. Okay, what's killing us now? Now, Discord and Firefox are predictably eating up a whole lot of resources. OBS is as well. But it shouldn't be that bad. I don't know why. I don't know why Pretzel Rocks just seems to have problems so much. Okay, well, no more music apparently. Hooray! Okay, so we get this oscillation toward equilibrium, which is going to, again, from here, going to get something that looks like this. It's going to have an exponential bound on both top and bottom. The top one here should be CE to the lambda t, actually A. AT. And A is less than 0, so we don't need to worry about that particular number there. And this is going to be negative CE to the AT as the lower bound there. In the case of pure oscillation, the only thing we have is going to be our sine cosine wave, whatever it is. And all of the peaks and troughs will be identically the same size forever and ever. It's going to be our, that's going to be our vertical stretch factor. Probably capital C in this case. Right, whatever the constants are that are sitting out front. And in theory, again, I feel like this thing should exist, but I'm not seeing it. So it is possible that our... Oh, yes, that's right. Okay, take a look at this, right? We've got negative gamma over 2m is going to be the real portion of this thing. So that will always have to be positive when we're talking about, our gamma amount here. This is a newtons per meter, I think. And this can only be a positive value. Just put the book on top of the surface I'm trying to write on. Okay, so negative gamma over 2m will always be less than 0, since gamma and m are both going to be strictly greater than 0. If m is equal to 0, then we got a problem, because you can't have a point mass that has no mass. And our gamma is going to be greater than 0 in this case, just because we're going to incorporate air resistance. If it's in a vacuum, you don't need that term. Just get rid of it. It's fine. It'll be an idealized system. Right, so we go back up here. Right. Right, so gamma is going to be 0 in a vacuum only. That's usually not the case. You can then worry about that when you are in space. right? And then we can't have this. So a cannot be greater than 0. That's our, again, gamma a is our negative gamma over 2m. I guess if I'm going to include it here, right, it could, in theory, be equal to 0. We'll just wait. Hang on. Right, greater than or equal to 0, and m must be strictly greater than 0. Okay, there we go. Doing better now. Then we go like this. We try to reopen that window. And let's see if it goes horribly. Yep, goes horribly. Okay. Nothing happened. Guess it's not that bad. Okay, so that's not what I want. Come on. Okay. Hey, and thank you everybody for the follows. I'm going to leave them anonymous for now, but if you would like to, you can feel free to sound off in chat and have a conversation about what we're doing tonight. We are doing differential equations. This is typically a sophomore level math, physics, engineering, basically any sciences that you're doing level class within the mathematics department. And definitely required for computer science, engineering, physics, mathematics, and any of the other like physical sciences, chemistry, things like that. They govern basically all behavior in the universe, and so it's really valuable to be able to try and figure out, at the very least, what kind of differential equation you are working with at any particular time. Whether or not there's a solution is a completely different question that you may have to answer. But at the very least, we can just say, like, what kind of differential equation do we have? What are we working with? And we are edging ever so closer to our follower goal of 500. So thank you so much, everybody. Tell your friends. My name is Obi-Wan Pez, and this is N-Simplex Pachinko. I do typically a lot of different stuff. So right now, what we're doing is we're doing my actual class that I taught called Differential Equations, which was taught at the community college level. So in America, this is a 2-year college experience, which will hopefully net you what's called an associate's degree. Typically, most students are going to go on to another 4-year university and complete their bachelor's degree. I believe that the AA degree, so Associate of Arts, AAS, Associate of Arts in Science, or the AS, Associate in Science degrees are typically going to be similar to the British A levels. So this is going to be usually an A level is 1 or 2 years on top of your GCSE schooling in a particular set of subjects. So this is if we want to equate it to the Wizarding World, your GCSEs are an awful lot like an owl, and A levels are an awful lot like Newt. So everything is now related to that particular book series. Anyway, Okay, so Monday, Wednesday, we are doing our differential equations class. And again, this is literally the same class that I taught in America to two-year students. Um, and our Tuesday nights are typically spent doing math help. So if I get on around the same time as usually Dawn does math, um, then we'll both do some sort of shout out to Dawn. Then we'll usually do some sort of math help for a while. Um, if I come to my computer far later and Dawn has already gotten like halfway through stream, oftentimes I'll just sit in his chat. I can help from there. It's fine. um, but it all depends. I usually do 9 p.m. or 2100 BST, which is our British summer time. I am an American. I am currently living in the UK. It is quite an experience. Very different from what I'm used to. Although still everybody speaks roughly the same language. Um, I got to tell you, listening to the Yorkshire accent is wild. Not quite as brain hurty as trying to listen to like the deep Scottish or Irish accents, which sometimes those guys come around and I'm just like, I hit me again. Let's I need to hear it again. Okay. Um, and this last set is also called underdamped. So if you think about this particular set of models, we can think of our door closing, as Zach had said earlier. If you have an overdamped system, then what's going to happen is this door is going to swing open, and then it's going to close maybe very quickly at first, and then just very slowly go toward R0, and maybe not actually reach actual equilibrium. It is also possible that our overdamped system, um, yeah, typically this is going to then close very slowly at the end. It may not actually ever move toward actual closure. It may end up stopping a little ways away. This was one of the cases of a lot of our doors in my community college because it just was not super great. Like the maintenance people only come by once every few weeks. You know, whenever they're there for something else, they'll be like, that door's not working quite right. Let me tweak it. The critically damped system, actually, let's talk about the other one. The underdamped system is going to be your door swings open and it swings closed. And it slams against the door frame, and it doesn't even give it the opportunity then to actually oscillate back and forth because it has an actual door stop there, right? The door frame is preventing it from then oscillating. This was the case in our door during my last semester at my community college. The door that was our like emergency exit, just like it was underdamped, i.e., there was pretty much nothing in. I'm wondering if somebody popped one of the screws on the I forget what that thing's called, the hydraulics, and it just like leaked all the hydraulic fluid out, because that would cause this thing to slam closed. So it is one possibility. Also, the underdamped system could be literally pure oscillation if, this is like, I mean, in real life, pure oscillation doesn't really happen, but it can happen for like reasonable amount of time. So those doors that swing both ways that you'd see in like a saloon, old-timey, old west saloon, that swing back and forth, those oftentimes were underdamped, but they were not pure oscillation. They would eventually start sinking down because their mechanism has in it a way in which the door is moving down as it's swinging this way, and once it reaches the bottom, it then has to swing back up again. And then it kind of like goes into this little divot, slows down because of friction. If you have one that was really, really super well greased, then you might have an underdamped system that our A value is extremely small. The critically damped system is pretty much what you want in almost every case. So if you think about it in terms of like the door example, this is going to open and then it's going to swing closed reasonably quickly and then slow down toward the end and just kind of go boop against the door frame nice and gently. There is also a secondary switch on those or secondary screw on those door hydraulics where you can change what'll happen and when it will happen. So, preferably not you, but the people who are in charge of maintenance and whatnot can actually go in and change the locations and speeds of these doors. Also, if you think of car shocks, for example, this is another case where we have a spring mass system. The mass is your car. The spring is these huge shocks that are sitting on either side of each of your wheels, and they help soften the motion of you getting bumped around on the road. So if you think about what happens after you hit a speed bump at like maybe a little quick of a speed, but not to the point where you're going to damage your car. An underdamped system on your car shocks would be awful. I have been in a few where it would essentially just keep going like this as you go past it, right? You hit this bump and you go whoop, 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 whoop. It's like, okay, this car needs to stop now. The overdamped system would be if your shocks were too good. So you'd hit this bump, and then the whole car would immediately just stop moving. And so it's a little bit jarring of an experience to be in an overdamped vehicle. Once you hit that bump, it may cause you to kind of drop into your seat just slightly, and then it feels like a harsh motion. Our critically damped system, on the other hand, again, you hit this bump, and then you just softly go back down again. Okay. So let's do one. So find the frequency of vibration of a 3 kilogram mass attached to a spring of Alright, give me that unit, because this does not look... That does not look nice to me. Dash pot, there we go. Okay, that was the word that Zach said earlier. Okay, so dash pots are those little hydraulics that are attached to doors. All right. This is saying that K1 is equal to 27. Oh, newtons per meter. There we go. The abbreviation's different, but yeah, it has to be newtons per meter. Right, if we do unit analysis on this, it also becomes pretty obvious. We're talking about the spring constant K. It's being multiplied by X. X is in meters. So if we want a force, F, right, which is going to be the same as this term, they have to have the same units going all the way across, then K is going to have to be newtons per meter times X, our meters, has to get us newtons, our force. All right, find the frequency of vibration of a 3 kilogram mass attached to a spring of K equals 27 newtons per meter. Well, that's fun. There's also another one that does a spring combination, so the two Ks are different from each other. We'll just do this one for now. Okay, so it's going to take 27 newtons to stretch this particular spring 1 meter. And again, our M here is going to be 3 kilograms. That's a big boy spring. At the very least, it stretches quite a bit. Okay, so what we're going to do here is we're going to look at our overall, oops, we're going to look at our overall equation here for differential equations. So 3x double prime plus, we're going to say that at the moment, this is not going to do anything for us. We didn't say that there was going to be any air resistance or anything like that. Plus kx, k is going to be 27, so 3x double prime plus 27x is going to be equal to 0. And again, this was not stated that it's negligible air friction, but there just was no information given. So we're going to assume that the frequency of vibration of this spring doesn't really matter whether there's air or not. All that's going to do is change the overall behavior of whether or not this is going to stop. So in this case, we can say, all right, let's divide by 3 So x double prime plus 9x is equal to 0. Our characteristic is going to then be lambda squared plus 9 is equal to 0. And so lambda is going to be equal to plus or minus 3i. And so this is going to be right, so our actual x is going to be equal to c1 cosine 3t plus c2 sine 3t. We discussed in our second order differential equations, this was how it's going to be. It's going to be a linear combination of our sines and cosines of our imaginary component of eigenvalues on the inside of our functions. So in this case, we end up with a function that has a frequency. Frequency typically denoted by omega? I think so. Wait, hang on. Omega is 3, but that doesn't tell us what the actual frequency is. Tau is the frequency. So omega is going to be equal to 2 pi over tau, which means that tau, our frequency, is going to be equal to 2 pi over 3 seconds. Okay, hang on. This is going to be 3 hertz, which is actually our frequency. That's better. This is going to be our wavelength. Or the period. All right, so how often is our wave going to come around back to the same exact spot that it was in at any arbitrary point? So the wavelength or the period of this thing is going to be 2 pi over 3 seconds. So that's roughly speaking about 2 seconds, give or take. And our omega is going to be 3 hertz. So things are a little bit different there. It's not really hertz like that. Damn it. Right, because hertz is wavelengths per second. So 3 is our comparative frequency. So this is going to be triple the default of triple, a third. Right, this is a third of our default, which is 2 pi seconds. So it's going to be 2 pi over 3 seconds. Our frequency is going to be 3 times faster than that default. Yeah. So the other, and feel free to yell at me if you don't like this one, but K2 for this case, they wanted to give K2 as 75 newtons per meter. So in this case, it's the same function, right? We still have 3 kilograms. Hmm. Or is it? Okay, so if we just do this as the default, as it's trying to do here, if this is just, oh, well, look, it's the same spring mass system, it's just a different spring. Right, this is 75 newtons per meter. Then this ends up with 3x double prime plus, again, 75x, same deal. So this ends up being x double prime plus 25x equals 0, which then, again, same deal, x squared plus 5 is, no, that's 25, equals 0, so lambda is going to be plus or minus 5i. So same thing, this is going to be x in this case is c1 cosine 5t plus c2 sine t, 5t, sine of 5t. I was going to write that regardless of what I actually said out loud. Hooray. So then, again, same thing here. This is going to have a frequency. Omega is 5. So this is 5 times faster than the default. Where omega is just equal to 1. And again, our tau is going to be equal to 2 pi over 5 seconds. So this one's 6 over 5-ish. So somewhere around 1.4, 1.5 seconds. Okay, so here's where I said, yell at me if you don't like it. The next question asks, what happens if these springs are tied together in parallel with the same 3 kilogram mass attached to it? And so what I'm seeing here is that individually we could treat them still as separate. This is one of the homework problems in this book, not something that's given. So, yay. So if we do this, right, I think that the way this is going to work is that we're still going to get 1.5 kilograms of force that's going to be gravitationally pulling on either side of this thing. and our 75 Newton per meter spring is just going to jiggle faster than our, what was the other one? 927. Newton per meter, which is going to more be like this or something. I mean, this may be extremely large because it's going to go up and down quite a bit. So this is going to spread its weight evenly amongst the two springs. Now, you may have issue with that, and I understand if that's the case. But I'm pretty sure that's how it's going to work. Or at least that is a reasonable approximation to make, rather than saying that our weight on either side, the mass that is distributed to each of the springs is going to be technically variable. I think that that's going to be awful. Now, I'm not really sure even necessarily how to I'm not even necessarily sure how to set this up. It's been so long since I even tried, right? That is what we would like to try and make it happen. How we want to try and make that happen. And then one of the other questions is what happens when you do it in series. So one hangs on the other, which in theory could actually be more simple. However, right, we still want to be able to figure this out either way. And this is, by the way, the same as you would work out multiple of our other systems. So not just oscillators, but also, yeah, pendulums also work. Yeah, tubes with water. That's like a U tube. God damn it. A tube in the shape of a U that has water in it. If it's like pumped in from the sink, and then it swings into this U-shaped trap at the bottom of your sink. Right? Like at what point will water that's higher on one side end up equalizing with the other? This ends up being an oscillatory motion as well. And typically this is going to oscillate. It's going to be damped oscillation in the same way that we have damped oscillation with springs. This damping force is going to cause it to slow down eventually. So it has been quite a while. we're just going to look this one up because I'm not going to spend that much time. Okay, it's just the sum of the forces, so easy enough. So m x double prime is going to be equal to the sum of all negative kx's on this side, where k is going to be I, and x is going to assume to be the same in theory. Maybe a terrible theory. In theory, this thing could be close enough that it's not going to wobble too much up and down. It's going to more or less hold the same distance all the way across it. Okay, so this is going to be m x double prime is equal to a negative 27x minus 75x. I feel like they shouldn't be easily combinable, but you know what? 3x double prime plus, this is going to be 102. X is equal to 0. Okay, divide by 3, x double prime plus, this is going to be 34. It's going to equal to 0, so here we have the characteristic lambda squared plus 34. 34 equals 0, and thus lambda is going to be plus or minus root 34I. So in this case, we're going to have a frequency. This means that lambda is going to be equal to root 34, and therefore tau is going to be 2 pi over root 34, which is almost 6, which means that we have about 6.28 divided by 6-ish, 5.9, 5.8. So we're going to get something 1.2, 1.3. Give or take. Okay. I mean, I don't feel terrible about it, but at the same time. Okay, so connected in parallel. And we can get the same thing, well, slightly different if they're connected in series. A question about that, right? Did we actually split this at all, or did we just call it 3 kilograms and it was just happened to be distributed? Okay, yeah. Whole system of springs behaves as a single spring with constant K. Yep. Okay. Again, makes sense. It's just slightly worrisome, like I might have done something wrong, but it's fine. Okay, in this case, this force upon each spring is equal to the applied force F. If each spring is deformed by an amount x sub I, the total deformation x is the sum of the deformation x sub I of each spring. N springs with respective constants k1, etc. are connected in series to an external force. This is making physics clear, by the way, so we'll throw them a shout out here, or not shout out. I can't necessarily speak to the whole site itself, but you know, seems reasonable. Okay. JP Mizrahi. It's not a very quick about us somewhere, so that's okay. Okay, so our x sub i's are going to all be equal to the x deformation of the full thing. So therefore, f over k is equal to all these things. So therefore, the equivalent spring constant 1 over k for the system in series is going to be equal to 1 over the sum of 1 over k sub I. Interesting. Okay. So this is going to be our 27 and 75. Doesn't really matter how they, which order or anything you do them in. It's all the same. So if we want the overall 1 over k total, it's going to be equal to 1 over 27 plus 1 over 75. So that's going to be a 75k plus 27k is going to be equal to the product of 27 and 75. All right, that's all threes, so that's going to be 81 times 25, which is going to be, why did I set it up that way? That's terrible. 81 times 25 is going to be 1600. 05 plus 20 and 400 for 20 is going to be 2025. Almost there. Right? I think that's right. Okay, so then this is going to be 102. 2025. 102 is made up of 3 and 34. 4, right? Because we just did that, yeah. 3 could be taken out from 2025. Leaving a 27 and a 25. And we don't have a 2, we don't have a 17, so that's going to be pretty ugly, but whatever. Okay, so 27 times 25 is going to be 675, divided by 34. That's our K total. $675 over 34 is going to be 19.85. And change. But. Right, newtons per meter. So the natural frequency of this thing is therefore going to be 3 x double prime plus k, 675 over 34, x equals 0. Divide by 3, 675 divided by 3 is going to be 220, right, yeah. X double prime plus 225 over 34, x. Characteristic, lambda squared plus this stuff. And therefore lambda is equal to plus or minus 15 over the square root of 34. And quite frankly, I'm just going to leave it there. I don't care. 15 divided by 34 square root is 5.83 is equal to 2.57. So omega is that value, 2.5725. And our relative frequency compared to our 2 pi is going to be that. That also means that 2 pi, right, 2 times pi divided by recall is going to be 2.44 seconds. Right, tau. Which also should make sense because these being connected in series to one another, this is going to cause one of them to stretch, and then the other one's going to stretch. It's attached to it. It's going to have a much larger stretch distance in total, under 3 kilograms of force, weight, mass. 3 kilograms of mass pulling down on it. All right. We'll get it someday. Okay, if we were to connect this whole system to a dash pot, right, 3 x double prime plus with a gamma of, at this point, it's not even going to look nice. So, 9. Right, I don't even know. It's plus the series example, so we end up with so 15 over root 34 as our k value. Is that our k value? No. 675 over 34. Times x is equal to, then if we leave it as 0, right, then we're going to still end up with this is a damped system. Because we do have a gamma. Right, gamma is going to be 9 in this case. And what are the units on this? So we need newtons are equal to kilogram meters per second squared. And x prime is meters per second. So this is gamma is equal to kilograms per second, which is equal to kilogram meter per second per meter. Squared. We still got squared? No. Right, take out meter per second. Is it newtons per meter per second? No. Maybe. Right, because if we do second squared second here, then we can end up with this part. Yeah. Newton per meter per second. Slightly convoluted, but yeah, I think that does actually make the most sense to use. Anyway. A force of 9 newtons for every meter per second that we're moving at. That seems like a lot. I don't know. We'll find out. Is it overdamped? Right, so we come in here, we say, let's do the same thing we did before, where we say this is going to be just x double prime plus 3x prime plus 225 over 34x equals 0. So now we want the characteristic, which is going to be lambda squared plus 3 lambda plus 225 over 34 is equal to 0. So lambda is going to be equal to negative 3 plus or minus square root of 9 minus 4 times 225 over 34. That's going to go with, that is going to be a 17 over 2 times 1. We don't have 1 there, so lambda is going to be equal to negative 3 plus or minus negative 3 halves if we want. plus or minus square root of all over 2. This is 9 minus 450 over 17. Okay. So we get a 26.47 subtracted from 9 is going to get us a negative 17.47. So yeah, this is going to be a big mess, but nonetheless. 9 times 17 is 153 minus 450. It's going to be 297 over 17. Over 17, 2 at the bottom. 297 divided by 17, I'm sure does not. Yeah, right. No. Does not come out nice. If we really wanted to mess with this, right? Could bring in the 2 as well. Put a factor of 4 on the bottom. Make it 68. This would be I 297 over 68. Everybody's like, why did you unrationalize the denominator? Oh. It's fine. Okay, so if this is lambda, then that means that the overall system is now going to be x is equal to c1 times cosine, nope, c1 times e to the negative 3/2 t times the cosine, come on, of square root 297 over 68 t plus c2 e to the negative 3/2 t times the sine of the same. So square root 297 over 68 times t. So if we have a damped system, this is going to be underdamped, and it's going to cause this particular thing to oscillate down to a 0 distance. But it's going to take a while. Right, if we wanted to see exactly where that puts us, yeah, it may not actually be that long. All right, so like C1 times y equals C1 times e to the negative 3/2 t, okay, x times cosine of square root fraction 297 over 68 x plus c2, yes, add sliders. It doesn't take that long. E to the negative 3/2 x sine of this thing over here copied into this bit over here. All right, it takes 2 seconds to get down to 0.06 meters. So, okay, fine. You're within 6 centimeters after 2 seconds. Right, and that never goes back up again. So we got our maximum here, our minimum here on the next oscillation. Okay, fine. Right, this is us starting at 0, 1, and it gets up to a maximum height of 1.02 meters. And this was when the spring mass system was in series, right? So they're stretching each other. Okay, and then we can change our C1 and our C2 accordingly. Oh, that's interesting. Yeah, okay. Destructive, constructive interference. That makes sense. So we're going to increase the values that we have there, or decrease the values we got there. Right, but still, we're very quickly approaching 0. When they were in parallel with each other, we got something slightly different, but again, I don't want to spend all of our time looking at that. We're already over time, so in theory, we'll probably stop here, and then on Wednesday, look at the other applications that I meant to get to tonight. But you know what? Spending a little bit of extra time here on examples is usually worthwhile, and we can see how these things play with each other. Again, when we connect it in parallel or in series, gets to be rather interesting. So I think I'm going to also do this in parallel, just off stream, and then show that in the in Discord as well. So anybody who's interested can stop on by Discord. We are using Penn Center's Discord, so don't do that. Penn Center is yet another math streamer, so if you would like to stop on by, speaking of Penn Center, he is also on, so we're going to go raid him. He is probably doing other mathy type stuff. I don't know actually whether he is streaming math for everybody or if it's for a class, but we will find out very quickly. So if you would all love to join on in, we will head on over to Penn Center's and linear functions. There's all sorts of stuff you could ask for over there. And so I sure hope y'all would love to come on and stop on in on tomorrow for random other math questions. If you have anything that you have, any particular if you have any other mathy type questions, come on in and we'll attempt to answer them. I typically like to make sure that students understand why things work. So there's going to be a lot of pushing to make students understand why in my streams, especially. Other people tend to also do it. It's just this is one of the things that I like to brag about, is that I really like to get students to understand why. Other than that, we will be back on, tomorrow, other math stuff. Wednesday, day 16 of differential equations, where we're going to talk about electricity and hopefully a few other things. We'll see how it goes. And then on Friday, we'll be back again for gamey type stuff. So we'll see where we're at. Probably going to be doing a bit more of Elite Dangerous, but we'll see.